Today's topic is Thevenins theorem. And Thevenins theorem is any two-terminal linear network containing energy source and impedance may be replaced by an equivalent circuit consisting of a voltage source E dash in series with the impedance Z dash, where E dash is the open circuit voltage measured between the terminal and Z dash is the impedance or equivalent impedance between the terminal when all energy sources have been replaced by their internal impedance. Here the linear network is the network which obey the Ohm's law. Ohm's law is, formula of the Ohm's law is V equals to IR. That means it is equivalent to Y equals to Mx also. And if we draw our characteristics, along x-axis is voltage, along y-axis is current, then the characteristics is straight line passing through the origin, that means linear. So the circuit, the current voltage characteristics of the circuit should be linear or straight line passing through the origin, and obviously must follow the Ohm's law V equals to IR. Then the circuit is called linear network, and obviously the circuit should contain the component resistance, capacitor or inductor, because diode, transistor, all these components are not the linear component because their current voltage characteristics are non-linear. And obviously a circuit containing energy source, it may be voltage source, it may be current source. This energy source may be voltage source, it may be current source. And impedance, that means resistance, capacitor or inductor. We consider a circuit which consists only voltage source E and the impedance or resistance ZA, ZB, ZC, and here ZL is the load impedance. And according to the Thevenins theorem, we can replace it by a equivalent circuit which consisting of a voltage source E dash and impedance Z dash, equivalent impedance Z dash, and ZL remain the same. So these two circuits are equivalent. These two circuits are equivalent. That means all the energy source of this circuit may be replaced by a equivalent energy source E dash. All the impedance of this circuit may be replaced by an equivalent impedance Z dash, and then we can say that this circuit is equivalent to this circuit where E dash energy source and Z dash are in series, and these two circuits obviously equivalent. So by using the Thevenins theorem, we can solve a complex circuit, and we can convert a complex circuit into a simple circuit, where a single this circuit contain a single energy source and single impedance or resistance, and this circuit is called Thevenin equivalent circuit. Now which we observe, we calculate the Thevenin equivalent resistance on Thevenin equivalent voltage, and we also prove these two circuits are equivalent, and we also calculate how to solve the Thevenin equivalent circuit, how to solve the current flowing through this Thevenin equivalent circuit. So consider I is the current flowing through mesh 1, and similarly we consider that IL is the current flowing through mesh 2. Suppose this one is the mesh 1 and this one is the mesh 2, and consider that IL dash is the current flowing through this Thevenin equivalent circuit. So from this circuit, from this Thevenin equivalent circuit, we can find that IL dash equals to E dash by Z dash plus ZL. E dash by Z dash plus ZL, where Z dash and ZL are in series. That's why Z dash plus ZL, and by using this formula, we can calculate the current flowing through the load resistance also for any numerical problem. Here E dash is called the Thevenin equivalent circuit, and this E dash sometimes represent as VTH, that means Thevenin voltage. Sometimes it is also represent as VOC, that means open circuit voltage. So E dash, VTH or VOC, open circuit voltage, all are same. And Z dash also can be represented as ZTH, Thevenin equivalent circuit, or sometimes it can written as RTH, Thevenin equivalent resistance. All are the same. So from this main circuit, suppose this one is figure 1 and this one is figure 2. From this figure 1, we can apply KVL. We can apply KVL. So E equals to, from the mesh 1, E equals to I ZA plus ZC. E equals to I ZA plus ZC, as I is flowing through ZA and ZC, minus ILZC. Why minus? Because ZC is common for both mesh 1 and mesh 2, and I is flowing through ZC. IL is also flowing through ZC, but in opposite direction. I is flowing through ZC, IL is also flowing through ZC, but in opposite direction. That's why minus ILZC. And we know that from KCL that if the two current are flowing in opposite direction, one is positive, another one is negative. That's why I and IL here, minus IL. From the mesh 2, 0 equals to, in this mesh, I is in the opposite direction of the IL, so minus of IZC and plus IL ZB plus ZC plus ZL. So these two equation we can get from main circuit by using the KVL. Now to find E dash or Z dash. E dash is the Thevenin equivalent circuit. To find this, E dash is the Thevenin equivalent voltage. To find this equivalent voltage, we have to remove the load resistance. So if we remove the load resistance, the circuit is this. Just remove the load resistance. So this is E, ZA, ZB, ZC. So to find E dash, we have to remove the load resistance. That means the current flowing through I, main circuit is, mesh 1 is I. If we connect a multimeter or voltmeter across these two terminal, the corresponding voltage of these two terminal is VTH, VOC or E dash. That means voltage across this open terminal is known as E dash or open circuit voltage or Thevenin equivalent voltage. So across this is known as VTH or VOC or E dash. Okay. So according to this theorem, E dash is equals to IZC, because if we measure the voltage across these two terminals, that means we can measure the voltage across the ZC. And I is the current flowing through ZC, so E dash equals to IZC. E dash equals to IZC, and I is the current flowing through mesh 1, so E upon ZA plus ZC multiply by ZC. So this is the Thevenin equivalent voltage E dash or VTH or open circuit voltage VOC. Now to find the equivalent resistance, that means Z dash or ZTH, so we have to shorted the voltage source. So voltage source is removed by a short circuit. If there is a current short, it should be open. That means to find the ZTH, the circuit is just like that. This is ZA, ZB and ZC. And the equivalent resistance is known as Z dash or ZTH. Equivalent resistance is known as Z dash or Thevenin equivalent resistance ZTH. So from this circuit diagram, the equivalent resistance of this circuit, that means ZA, ZB, ZC, and from this diagram, ZA and ZC both are parallel and ZB is series with them. So Z dash or ZTH is equals to ZA parallel ZC in series ZB. So ZA ZC by ZA plus ZC plus ZB. So this is the equivalent resistance or Thevenin equivalent resistance. Equivalent resistance or Thevenin equivalent. Now solve these two equations. Equation 1 and 2. Solve these two equations by using Cramer's rule. By using Cramer's rule. Solve this equation by using Cramer's rule. We find the value of IL. We find the value of IL. So first numerator contains ZA plus ZC and minus of ZC, and as we find IL, so next column is E and 0. Denominator contains ZA plus ZC minus ZC minus ZC ZB plus ZB plus ZC plus ZL. So these are the denominator form. So now solve it. 0 minus of minus EZC ZA plus ZC ZB plus ZC plus ZL minus and minus minus plus, so ZC square. So numerator is EZC upon multiply these two bracket, so ZB ZA plus ZC ZC multiplied with ZA ZC plus of ZC multiplied with ZC. Only this term multiply, ZC multiplied with ZA and ZC multiplied with ZC plus ZA plus ZC ZL minus of ZC square. This ZC square. So these two are cancelled. So divide each term of the numerator and denominator by ZA plus ZC. So ZA plus ZC divide this term by ZA plus ZC, that means ZB ZA ZC upon ZA plus ZC, and this also, if we divide this term with ZA plus ZC, so ZL. So this numerator term is equivalent to E dashed. This numerator term equivalent to E dashed. So it is equivalent to E dashed, and in denominator ZB plus ZA ZC by ZA plus ZC is Z dashed plus ZL, and this is equivalent to the current flowing through this equivalent circuit, that means IL dashed. So this is IL equals to E dashed by Z dash plus ZL, and IL dash is also E dashed upon Z dash plus ZL. So this is IL equals to IL dashed. So Thevenin's theorem proved, and from this calculation we can also observe that how we find the Thevenin equivalent circuit, how we calculate the Thevenin equivalent resistance. So these two are the very important to calculate the Thevenin voltage and Thevenin resistance. And after calculating Thevenin equivalent voltage and Thevenin equivalent resistance, if we put the value of Z dash and ZL in this equation, Z dash ZL in this equation and E dash in this from this calculation in this equation, then we get the value of IL dash, and IL dash is the current flowing through the Thevenin equivalent resistance or current flowing through the load resistance. So these three formula are very important to solve any numerical using the Thevenin's theorem. So you have to keep in mind that to find the Thevenin equivalent voltage, just remove the load resistance ZL and find the voltage across this open terminal by using either KVL or KCL or any kind of method. And to find the load resistance or equivalent resistance, to find the equivalent resistance or Thevenin equivalent resistance, just remove the voltage source by a short circuit, and if there is a current source, then just open this current source, then calculate the Thevenin equivalent resistance by using this all these resistance. They are series or parallel, ZA, ZB, ZC and series and parallel. Some number of resistance are available in the circuit, and we can also calculate the equivalent resistance like series and parallel resistance. So you get the value of Thevenin equivalent resistance, and after that you put the value Z dashed and E dashed, and obviously from this circuit you know the value of load resistance and calculate the IL dashed also. So in this method we can solve any simple circuit by using a Thevenin's theorem. Thank you.